In today's lesson, we are going to be looking at transformations of exponential functions. So we've already looked at transformations for some of our three main parent functions, right? Our quadratic, our rational, and our radical. We're going to be taking those same transformations and incorporating it into a new parent function, which is our exponential function. So the same transformations just applied to a different parental or parent function. So just as a little bit of a warm-up, try to go through and think about which of the following graphs below are the same. Right, so think about your power laws and just kind of use this as a little bit of a warm-up to see which graphs are going to be the same. Because in some cases with our transformations, we might be able to apply some specific changes to our function or write it in different ways. Try to go through and think about which ones are the same here. So with our transformations, right, as I mentioned before, these exponential functions can be transformed in the same way as other functions, right? In this case, when we're dealing with an exponential function and we're talking about the parent function, we are going to be referring to y equals b to the power of x. So now I know in our previous lessons we talked about the exponential function being y equals a b to the power of x, but a is actually part of our transformation. Right, so our general parent function is just going to be y equals b to the power of x. And if we see here, this is what our transformed function or the general transformed function is going to look like. Y equals ab to the power of k times x minus d plus c. So again, very similar to the other transformations, the transformations that are affecting the x or the horizontal. Right, they apply to where the x is, so they should be up in this exponent. So we see the k and the d in the exponent, the a and the c, because they are vertical changes or they affect the y value, they're not attached to the x or associated with the x, so to speak. So this is going to be our general transformed function for the exponential. And again, we'll just review this, but those changes that we talked about, the different variables, a, k, d, and c, they're the same as the other ones, right? So it's the same transformations, the same kind of characteristics that we're looking for, right? C represents our vertical translation, right? So if c is going to be less than 0 or negative, we'll put that in there here, then it shifts down. If it's greater than 0 or positive, it shifts up. For our a value, a represents the vertical stretch or compression, right? So if a is greater than 1 or less than -1, so basically if it is a whole number, so to speak, I'll put in quotations whole number, right? Then it is a vertical stretch by a factor of 0. Or by a factor of whatever a is. Sorry. If a is between -1 and 1, right? So if it's some sort of decimal, right, then it is a vertical compression by a factor of a. And if a is less than 0 or negative, then we have a vertical reflection, which means a reflection over the x-axis. Because if it's reflecting over the x, that is referring to then a vertical reflection. It's reflected vertically. Which again, these are the same as the other transformations that we looked at in the previous unit. For the horizontal or the changes to the x value or the x coordinates, d represents our horizontal translation, right? If it is a negative, then it shifts left. If it's a positive, it shifts right. Now, however, we do want to make the note, it appears as the opposite in our function. Right, so just a reminder that these values are going to appear as the opposite, right? So in our function, it might be a positive. in a d value, or it looks like a positive, but that means it's actually negative because our general form has a minus d in it. So when you minus a negative, that actually appears as positive. When you minus a positive, it appears as negative. So we just want to keep that in mind, give us that reminder. For K, the horizontal stretch or compression, again, similar to our other types or the other K values that we looked at, right? If K is greater than 1 or less than -1. So again, not a whole number, so to speak, but a number that is 1 point something and larger, right? That means it's a vertical compression by a factor of 1 over K, right? So we still have to do that 1 over K to determine what it's going to be. In our equation, we might see it as a whole number, but that means it is a compression. If it is a decimal, right, so it's between -1 and 1, that's a horizontal stretch by a factor of 1 over K. So we still have to do that 1 over K, even though it's an exponential. That doesn't change what we have to do to our transformations. And if K is negative, right, it's still a horizontal reflection, which means a reflection over the y-axis. So it's reflecting horizontally, so it's reflecting over the x-axis. Or y, sorry, I keep messing that up. Horizontal reflection over the y-axis. Again, these are all the same. So if you need a reminder, you can look back here, or you can go and review your notes from the previous unit that looked at transformations. But all these variables, the A, K, D, and C, they all represent the same type of transformation. Again, don't forget that order of the transformations matter, right? So again, it does help that we read it left to right. So we do the reflections, the stretches, and compressions first, then do the horizontal and vertical shifts. So A, K, D, and C, right? Exactly in the order as we see it in our function. And again, this is the same as it was for the other parent functions in the previous unit. So let's go through and look at an example. We want to graph the function g at x is equal to 2 times 2 to the power of 1/2 x minus 1. So this is a different step than what we've had to deal with before. We want to look and figure out what is the base function. Right? And remember, the base function was in the form y equals b to the power of x. So if I look at this function, the 2 is the power that is, or the 2 is the number that is raised to an exponent. So that 2 is our b, or the base of this exponential function. So our base function is actually y equals 2 to the power of x. That means that anything that is not that 2 to the power of x is going to be a transformation. It should be one of those variables. So let's go through and describe the transformations made to this base function. So we have, I'll just write it here again, y equals 2 times 2 to the power of 1/2 x minus 1. Right, so the 2 here, this is our part of our base function, and so is the x. So I'm going to look, I do have an a value of 2. So a is 2. This tells me, let me just do it. This tells me because it's a whole number and it's positive, we have a vertical stretch by a factor of 2. We then have a half, and this is our k value, so k equals 1 over 2. This means that the factor that we apply is going to be 1 over a half, or 1 divided by a half. So this means, because we have a decimal here, it actually implies the opposite. So we have a horizontal stretch by a factor of, and it's 1 over k, or 1 over 1/2, which is by a factor of 2. So again, kind of opposite of what we see. And we have a minus 1, so this means we have a d value of positive 1. So we shift right 1 unit. And those are the 3 transformations to our base or parent function. Now what we want to do, we want to create a table of values. So we want to go through, kind of create our table of values, come up with our image points, and determine what our transformed function is going to look like. So this is where I'm going to need my mapping notation to kind of help. I have my f at x on one side, my mapping notation on the other side. Well, because I'm stretching x by a factor of 2, it's going to be 2x, and then we shift right, so plus 1. For the y value, it's just a vertical stretch, so just 2y. For our key points, we're going to do -3, -2, -1, 0, 1, 2. Missing the third one. Just add it in down there, so we'll have 3. So then now I can go through, okay, my a value or my y value, keeping in mind that our parent function here, the f at x, is equal to 2 to the power of x. Right, so this is important. So the key points, the x values can stay the same, but our y values are going to vary depending on what the base function is. That's why we also needed to determine what the base function was. Because I need to take all of these points and plug them into this function. So 2 to the power of -3 is 1 over 8. 2 to the power of -2 is 1 over 4. 1 over 2, 1, 2, 4, and 8. So all I'm doing is I'm plugging the value into, or each x value into this function. Or you can think of, well, if my b value is 2, that means it doubles. So I'm just starting off, I have one value and it's doubling every time. For my transformed function now, let me just draw on this bottom part here. For my transformed function now I'm going to go through and apply these transformations. Actually, let me put them in a different color. And apply these transformations to each of these values. So -3 times 2, we'll do the first one, -3, or technically 2 times -3 plus 1 is equal to -5. And then 2 times 1 over 8 is 1/4. And I'm going to do that for every set of points. So the next one we get -3, -1, 1, 3, 5, and 7. And on the opposite side, we have 1/2, 1, 2, 4, 8, and 16. Now the nice thing is, because it's exponential and these values have to have the same ratio, right? We need to see this factor every time. We should see that it's doubling, right? Times 2, times 2, times 2, times 2. So even though it's transformed, it should still carry the same ratio because our b value hasn't changed. So now that I have those two functions, I can go through and I can plot them on my graph. I'm going to plot both of them in this case just to get an idea of it. So we're at -3 and 1/8, so very small, -4 1/4, or sorry, -2 1/4, -1 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Not very good. So there's my parent function, f at x. Let me keep it color-coded. We'll keep it color-coded for this. R's are actually backwards. Actually, let me just go back. We'll change it up quickly just to keep it consistent with what is on the next page. So I have my parent function f at x. I'm going to go through and plot my image points for my transform function. So -5 1/2, or sorry, -5 1/4. Oops, I'll go back and draw the red line in later. -3 1/2, -1 and 1, 1 and 2, 3 and 4, 5 and 8, and 7 and 16. So there's my transformed function g at x. Go back in and draw a line for my parent function. There's my parent function f at x. So you see a little bit of a change there, but we do have our transformation now as well. So we can see the transformation, we can see the different changes in these functions. Let's do it again for the next one. Right, so graph the function g at x equals 3 times 2x minus 4 plus 1. So this one's a little bit different because we don't clearly see a k value being outside the bracket, right? And it should be a k times x minus d, something like that. So if this is the case, sometimes the k value might have to be common factored out. And as additional note, the c value tells us the horizontal asymptote. So the c value tells us what is that value that our graph approaches but doesn't quite touch. Again, we want to determine first the base function. So the base function is going to be what is our b value. In this case, our b value is 3. So our base function will be y equals 3 to the power of x. So that's going to be helpful when we go to graph because we need to come up with our parent function and then our image points. What transformations are made to the base function? So I'm going to write out our base function again, 3, 2 to the power of x minus 4 plus 1. However, we need to common factor that k value out. So our actual function is going to be y equals, not 2x minus 4. Our actual base or actual transform function is going to be y equals 3 to the power of, I'm going to take 2 as a common factor out, x minus 2 plus 1. So now I can clearly see my 3 values that are going to represent the transformations. So I have a k value of 2. So that means I have a, not a vertical, a horizontal compression by a factor of 1 over 2, because it's 1 over k for our factor. Our d value is equal to positive 2, opposite of what we see. So this means that we shift right 2. And our c value is equal to 1, so this means we shift up 1. So those are our 3 transformations. I'm going to make a table of values based off of that parent function. Probably going to have to add in another row for each one. So we have our parent function, our f at x equals 3x. And then we have our transformed function, which for our image points, we call it g at x, or image points. So x is being multiplied by a half, and we're adding 2. And for our y value, we're just adding 1. So for our x value, so we have, or for our parent function, we have -3, -2, -1, 0, 1, 2, 3. So we have 1 over 27, 1 over 9, 1 over 3. We have 1, 3, 9, 27. And then for our transformed function, right, -3 times a half plus 2 is 0.5. And we have 1, 1.5, 2, 2.5, 3, and 3.5. So for a y value, we're going to be adding 1 to everything. I'm going to leave it as decimals just because it's a little bit easier to write out. adding 1 to everything, 2, 4, 10, 28. This one we don't actually see that change in the y, but that's probably because we've added 1 every time. We don't see that same ratio, so to speak. Or perhaps I'm just not looking at it properly. Yeah, it's going to be a little bit different because we are adding to it, so that is going to change it. So we might not actually see that ratio every time, but we're just going to trust our transformations and trust our values. So I have all of those values. When I go through now, I'm just wanting to graph the transformed function in this case. So I'm just going to go through and plot the points. So when x is a half, 2, 1, so a half, it was 1.4 or 1.04. At 1, it was 1.11. At 1.5 is about 1.3. At 2, it was 2. 2.5, it was 4. 3, it was 10. And 3.5, it was 28, which is going to be off our graph. And this one, we don't have any of the other values before, but if we scroll back up, it did say that our C value is the horizontal asymptote. So that means if I look, our C value is +1. So I should have a horizontal line coming across here at +1. Right, this is my asymptote. At y equals 1. Right? So this tells me that's the line that it's approaching. So when I graph it, it's never going to touch that line. It's going to get very, very close to it, but it's not going to quite touch. And that's my parent function, or my transformed function. We can do one last example. Right? Third example, similar idea. Going to go through, we want to figure out our base function. So our base function in this case is the 1/2, so y equals 1/2 x. So that's our base function. The transformations, there's nothing fancy we have to do with this one, so I'm just going to rewrite it. Don't have to do any factoring. I'm going to go through, look at all my values to figure out what my transformations are going to be. I have an a value of -2, so this means I have a vertical stretch by a factor of 2, not -2, because the negative does not apply. The negative does not contribute to the stretch. The negative actually, though, does imply a vertical reflection, right? Or a reflection over the x-axis. So the negative has something else that it does. It doesn't apply to or doesn't contribute to the stretch. We have a d value of +2, so this means we shift left 2, and our c value is -2, so we shift down 2, right? This is also the asymptote at y equals -2, just if we want that kind of reminder as well. I need to make my parent functions and my image points. Again, I'm going to draw in my table because I messed those up by not adding one column. Again, that one extra one might not really matter just because of the exponential growth. It might be too small to really even draw anyways, or too large, but we'll have it in there just for argument's sake and keep it consistent. So -3, -2, -1, 0, 1, 2, 3. And again, remember our parent function, f at x is equal to 1/2 to the power of x. Right, so I could just take my values and plug them in. So -3, or 1/2 to the power of -3 is 8, then 4, then 2, then 1, then 1/2, 1/4, and 1/8, which which makes sense because I'm dividing by 2 every time. For our transformed function, our g at x, right? Our g at x, we're going to have our x value. X value. I made a mistake. It's not left 2. It's right 2. So plus 2. This one. Or did I not? I didn't even write it out right. My mistake. So it's not negative 3. Or it is negative 3. I wrote down negative 2 for some reason, which means that the d value is 3, which means we shift right 3. So I apologize for that. Hopefully it's not too much for you to change that. So we go back. Our transform function for x is plus 3. For y, it's going to be negative 2 times y minus 2. And again, if we forget our mapping notation, right, x divided by k plus d, ay plus c. So just remember that mapping notation when you're going through and filling out the image points for the transformed function. So we're adding 3 to all of our values for x. So we have 0, 1, 2, 3, 4, 5, and 6. And for the y values, we're multiplying them by negative 2 and adding, and then taking away 2. So 18 times negative 2 is negative 16, minus 2 is negative 18. And negative 10, negative 6, negative 4, negative 3, negative 2.5, negative 2.25. So again, just taking those values and applying the transformations to them. Now that I have all of those values, now I can go through and graph. Right? So I can graph all these points. So at 0 and negative 18, at 1 and negative 10, at 2 and negative 6, 3 and negative 4, 4 and negative 2.5, and 6 and negative 2.25. And we do need to have our asymptote in here to make it a little bit easier to draw. Right? So I'm going to draw my asymptote at y equals negative 2, which we already mentioned that's what it was. Or our c value. So then now it's a little bit easier for me to sketch because I know what it's going to approach. Oops. Go back the other way. And again, I am roughly sketching it, but I do need to make sure that I have at least those key points, those image points down. And there is my transformed function. So with these transformations, very similar to the transformations from other values, right? Or from our other functions or other parent functions. We need to keep in mind, right, that for our parent function, it is in the general form y equals a or y equals b to the power of x. So there are going to be different parent functions for every kind of exponential graph. It all depends on what the b value is. So it's not like the quadratic or the rational or the radical, where we had the same parent function or the same key points for every transformation. Right? If you look back at this one, right, example 3, example 2, example 1, our parent function or those key points for those parent functions were different for all 3 because we had different b values. So that's the extra step. The transformations are the same as they are for the other functions. They're applied the same. So everything that we did with the those 3 main functions in the last unit will apply to the exponential function here.